Okay, so good morning, everyone, and welcome to this NISQ webinar. So I'm Pascal Bernier-Bruna. I am the communication manager for Project NISQ, and today our subject is quantum computing for optimization problems, and we have invited Yannick Chatterjee from Total Energy. So, sorry, trying to go to the next slide, but for some reason, yep. Okay, so this webinar is one of a series. Our objective is to help the quantum community discover and test the libraries and the tools that NISQ is making available, and to get your feedback. So we have already had a number of webinars, and by the way, they have all been recorded. So don't hesitate to go to our website to check what's available. And we are going to continue our monthly webinar until the end of the year. So we already have another one scheduled for September about hard optimization problems for smart charging of electric vehicles. So registration is open. Don't hesitate to go to our website. And in October, we'll have quantum rule-based systems for breast cancer detection. Registration is not open yet, but we will open it soon. And we, as you know, we send emails to our regular attendants so that they have the information. So enough about our webinars in general. Let's go to today's subject and today's speaker. So welcome, Yannick. Thank you for accepting to be our speaker today. So Yannick is a final year PhD candidate at Total Energy, and actually he told me he submitted his thesis this week. So
yes.
He's been working on this for 3 years. Is that it, Yannick?
Yeah. Yes.
Okay.
Yes.
Okay. So welcome, Yannick. Also, I have put here the related publications for today's webinar. Yannick will mention them too in his presentation. And yes, important point, I will send the slides to everyone after the webinar. So you will also get the link to the recording. So without any further ado, Yannick, I will stop sharing and it's your turn.
Okay, so wait, I'm just gonna share current slide. Okay, yeah. So I guess it's working, right?
Yes, it is
okay.
Working.
Great. So I'm gonna just wait a minute. Okay, perfect. So I'm gonna talk about what I did kind of sorry, it's not okay, fine. Okay, so I'm going to talk about what we did in terms of task 5.4 as part of my PhD as well. And yeah, so firstly, I'm going to talk about this novel method, the new method to encode optimization problems on quantum computers that we developed. We call this the LogQ encoding. And finally, after that, I'm going to also talk about the use case in terms of the task 5.4 and deliverable 5.9 and 5.11, I guess. So I'm going to talk about all these things. So okay, why is it? Okay, the second, so next I'm going to talk about what is optimization. So in optimization, simply we have to maximize or minimize a function, any multivariable function having x1 to xn multiple variables, and we want to maximize or minimize it. And this function we call an objective function. And then combinatorial optimization is a specific type of optimization where the variables are discrete. So they are integers. So all the problems that I'm going to show here are going to be binary. So 0, 1 or -1, 1. So they're going to be binary, 2 states. But in general, they can be integer as well. On top of that, there are constraints on the variables. So there can be constraints on the variables, which are just relations between variables. So relations in terms of they can be equalities, they can also be inequalities. So constraints on the variables, they limit the search space. They limit the feasible space, the feasible solution space. And finally, the motivation, why are we trying these kind of optimization problems on quantum computers? It's because basically a lot of these problems are NP hard. What does this mean? It means that most of these problems, a lot of these problems don't have a polynomial time algorithm, which means as the size of the problem increases, the time taken by the algorithm increases exponentially. So finally, for a large enough problem, we are not able to solve it on a computer, on a classical supercomputer. So that's why that is a motivation to try to develop quantum algorithm for such problems. One such NP-hard problem is called the maximum cut problem. A maximum cut problem is a graph problem. So where the idea is to maximize the number of cuts. So the cut is our objective function. So what is a cut? Here I have two graphs shown. So let's look at the top graph. I have 5 nodes and 6 edges. So out of these 6 edges, we have to check which of the edges have two vertices in different subsets. So we have bipartitioned this graph into black nodes and white nodes. And for example, 5 of these edges, as you can see, they're colored. They have nodes in different subsets, one black and white. So the cut in this case will be 5. So similarly, the edges can also be weighted. That what we're going to use actually is the weighted max cut. The weighted max cut, what happens is the edges are weighted and we have to maximize the weight of the edges. So basically you count the number of, count the weight, and it's 25 here for the colored ones. Okay, and now these things can be represented, these solutions can be represented as a vector. So what is a vector? It's like the representation of the solution, and it can be in terms of, as I said before, binary. So 1 0 1 0 1. So how is it 1 0 1 0 1? Just start with the leftmost node, and if I say the 1 is the black nodes and 0 is the white nodes, then I will say 1 0, and I go in a clockwise manner. Then I can say it's 1 0 1 0 1. Important note: maximum cut is also a symmetric problem, which means if I say that 0 is the black node and 1 is the white node, so and I go and I say it's 0 1 0 1 0, that's also an equivalent representation of the solution. So any complementary solution is also a representation of the solution. So max cut will always have 2 solutions in that sense. After that, equivalently, we can also represent it as a -1 and 1. Which will be very important in our formulation in the future slides. So equivalently, we can say 1 is black or -1 is white, something like that. So that's the representation. Okay, so now I'm gonna dive a bit into the algorithm that we're doing and why we're doing it. So it's because we need to be efficient in terms of qubits when we develop our algorithms. So most algorithms, so QAOA, as you know, is widely studied, as you might know, it's a widely studied quantum optimization algorithm. So it scales linearly in the sense that if I have 200 vertex max cut, I will need 200 qubits to solve it. But the problem is today, there are very few qubits available, and even if we have hundreds of qubits, sometimes they are not all in all connected or well connected, which means that we will not be able to use the power of all these qubits. So that was a motivation to develop an algorithm that reduces significantly the number of qubits. So the algorithm that I'm gonna, the encoding or the algorithm that I'm gonna present here is gonna require much fewer number of qubits, which means if I have 7 qubits, I'll be able to solve and represent a problem of 200 of 120 size, and with 8 qubits, it's 250, something like that. So yeah, that is the motivation. Next, okay. So next, a definition: what is a Laplacian matrix of a graph? Every graph has a related Laplacian matrix. A Laplacian matrix, as you can see here, is a matrix where in the diagonal elements we're going to have the weighted degree. So let's see for the first element. So that for the node 1, you have the sum of the weights is 3.3 plus 1, 4. For 2, it's 8 plus 3, it's 11, and so on and so forth. And then we have the off-diagonal elements, which are the negative of the weights of the edge. For example, the edge 1, 2. So if you go to the first row and the second column, it will be -3, and so on. So it's negative of the edge, negative of the adjacency term, negative of the adjacency term, as we say. And otherwise, if there is no edge, it will be 0. So every graph can be represented in terms of a Laplacian matrix. Okay. So the graph, the max cut problem that I presented to you before can be presented. The cost function for the number of cuts can be represented using the Laplacian matrix. In order to do this, we're gonna need to represent our solution in terms of ones and minus ones, as I showed before as well. So ones and minus ones, this vector will have the same size as the number of nodes of the graph. And if you represent it like this, then the cost function, it can be verified, will be 1/4 x transpose Lx, where x, as I said, is the vector and L is the Laplacian matrix. Okay, so we have this formula, this classical formula. It's a classical relation. Till now, I have not gone anything into quantum. And now we can take idea from we can take an idea from this equation and say, okay, maybe I can represent this equation on the quantum computer. How? Because psi, our vector, our quantum state, is also a vector. L is a matrix, which is an operator, and the bra of psi, of course, is a transpose. So psi L psi. So the expectation value of L in the state psi is equivalent to finding x transpose Lx. Will be equivalent to finding the number of cuts of the graph or the cost function of our problem. Okay, and the 2 to the power n minus 2 you see here is the multiplication for normalization. Okay, and so the interesting thing here is that to represent this problem of n size n, you will require log n qubits. How? It's quite, if you think about it, if you have a 1 qubit gate, for example, it's a 2x2 matrix. If you have a 2 qubit gate, it's a 4x4 matrix, and so on. So if you have an n qubit gate, if you have an n qubit matrix, it's a 2 to the power n. If you have 3 qubits, you can represent 2 to the power. If you have n qubit gate, you can represent 2 to the power n cross 2 power n matrix. So similarly, so that's why using this logic, if I have if you have to find the expectation value of an n cross n matrix, you would require only log n qubits. Okay, so this equation that I said, C theta 1 to theta n equal to psi L psi it is parameterized. So it's a parameterized representation of the equation on the quantum computer. Okay, so now we have to create an ansatz. So what is the ansatz? Ansatz is just the state. The ansatz represents all the solutions of the max cut, right? So how are we gonna create the ansatz? We're gonna take the 0 and we're gonna take n qubits, so 0 n, and then we're gonna put n Hadamard gates, and there is a unitary gate, u of theta, where theta is theta 1 to theta n. And u of theta is a diagonal gate, which is defined as follows: e to the power I by r, theta 1 is by r by r, I by r theta 2, and so on and so forth, where r converts continuous variables to, so theta is a continuous variable. In our algorithm, we fixed it to be between 0 and 2 pi, and r will just convert it to 0 and 1. Similarly, e to the power I pi r is going to convert it to 1 and -1. So finally, these diagonal terms are finally going to be just 1 and -1. So let's take an example to see this. So take the same example of the graph that we saw, and let's take the values of thetas to be, let's say, 0.5 pi, 1.2 pi, 1.4 pi, and 0.7 pi. So these values of theta should represent a solution, should represent the same solution as in red, as you see here. So how will it do that? It's r of theta. R of theta, as I said, if it's, as we saw before, if it's 0 to pi, r will make it 0. And if it's pi to 2 pi, it will be 1. So these values of theta represents 0, 1, 1, 0. And e to the power I pi of r will be 1, -1, -1, 1. And therefore our our answer, our unitary diagonal gate becomes 1, -1, -1, 1. So finally, combining all this, we have the ansatz as follows. This is the ansatz for a 4-node max cut problem using 2 qubits. Okay, so once we have our ansatz, here's the overview of the algorithm. So first we start with, on the left with our ansatz, we create the initial ansatz. And then the next part is you have to calculate the expectation value of a Hamiltonian. So the Hamiltonian will depend on the problem. But for the max cut problem, the Hamiltonian is -L. So as I said before, we have to calculate the expectation value of the Laplacian. The negative sign is because our classical black box optimizers usually minimize. So that's why I put L, minus of L. Okay. So the variational ansatz will not change whatever the problem is, basically. Now I've only spoken about max cut, but later I'll speak about other problems as well. So basically, it will never change. The ansatz for the algorithm remains the same. Why I'm mentioning this? Because this is in contrast with QAOA, if you know about it, where the ansatz depends on the problem. So here, I'm not encoding my problem in the ansatz. The problem is encoded only in the expectation value of the operator that I choose to calculate my expectation value. Okay. So first step, create the ansatz. Second step, enter the operator, calculate the expectation value of the operator, and then send the parameters theta to the classical optimization loop. Optimize as long as you have sufficiently good, well, we don't have a proof for optimality here because it's a heuristic. So you run it as long as you have a sufficiently good solution. And then you take the best theta, and the best theta gives us the theta that we have. Let's say theta, we call it theta star, the theta that we get at the end of our optimization circuit. And from this theta, we will find the solution. As we saw before, for whatever the value of theta that we get, we can find the solution from that. So yeah, so we will get the final theta, and this will give us the final solution. Okay, so some results. So results for 32 nodes here. So requires 5 qubits. This was done on the quantum simulator. So this is different densities plotted for size of all of size 32. And it shows that the algorithm does not, like the performance does not degrade with increasing density. It even gets better especially for 1, it's quite easy. But it remains quite good for multiple densities. Now for 64 nodes requires 6 qubits. And here we have results for both simulator and QPU. The ILP here is the integer linear program, and GW is the Gummins-Williamson algorithm. So for ILP, the solution is optimal. So the algorithm was run to optimality. So you can compare the solution here. And the approximation ratio for most cases was around 91 or 92%. And for QPU, it was a bit degraded. of course, due to the noise, and we got results of around 80%. Okay, and then we have results for 128 and 256 nodes that required 7 and 8 qubits each. So for simulator, we have, so here you can see that we're comparing with the GW bound, and that the percentages are a bit less, around 83%. Actually, it doesn't mean that the results actually degraded. It's just previously we were comparing with the ILP optimal solution, and this is just, we're just comparing with the GW upper bound. So upper bound is actually more than the optimal. And this is calculated by the Gummins-Williamson method. We take an average of the Gummins-Williamson method to give the upper bound. And similarly for QPU, we can see it's around 82, 85%, and around 90% for 256. Okay. So, okay, so well and good. We tried to do a max-cut problem. That's one problem. Now the next question arises, okay, can we solve more problems with this method? And what can we do to solve more problems? So a rather straightforward way to do this would be to convert other problems to the max-cut problem. As you can see in the graph, this is a graph of a number of NP-complete problems that can all be connected to max-cut from one level or another. And theoretically, all problems from the NP-complete class can be connected to each other, but it's not always straightforward to do, but theoretically can be done. So an example for this is number partitioning. So let's say what number partitioning is another NP-hard problem, and it is defined as follows. Given a set of integers, you have to bipartition it so as to minimize the difference of the sums. So simply, for example, you have 4 numbers, 2, 3, 4, and 10. So what you do, you divide into 2 sets. One is 10 and one is 2, 3, 4. You sum them both. So on one side we have 10, and the other side we have 2 plus 3 plus 4. And finally, it is the objective function is 1 here. And this is actually the minimum partition for this case. It's easily visible, but for larger number of numbers, it's not as obvious. And now we're going to convert this problem into the maximum cut problem. So in order to do this, so we have the same numbers. We take the same example. So 2, 3, 4, and 10. For every number, you take a node of a graph, and we connect each of them to each of them. So we connect. It's an all-in-all connected graph. And after that, what we do, we add a weight is equal to the product of the numbers. So 2 and 4 we connect, and the weight of the edge is 2 times 4. Similarly, we connect 4 and 3, it's 4 times 3, and so on and so forth. And it gives the following graph with 4 nodes, A, B, C, D, and the weights, as you can see. And this problem, the max cut of this problem can be proved to be exactly the same as the value of the max cut of this problem is exactly the same as the value of the difference of sums in a number partitioning problem. So that is how you convert one problem to another. So some results. So here we can see that most of the time we get an optimal solution, and this is coherent with what we saw before, that as we increase density, the best density had almost 1, like almost very good results. And therefore, and also we saw before that for the number partitioning, it's an all-in-all connected graph. So it's a fully dense graph. So it's kind of makes sense that we have such good results. So it's almost always optimal. And for QPU, the average was 93, and with the variance, as you can see. Okay, so for every problem, it might not be easy to convert to max cut. it might not be straightforward to convert every problem to max-cut. And as you can see, sometimes there are multiple layers. Sometimes it might not be possible even. Well, theoretically it is possible, but it might not be practically it can be practically quite hard. So for those times, what we can do is that's why we propose like a generalization. So a generalization to a QUBO problem. So any problem, we propose that any problem that we can represent in terms of QUBO. So quadratic unconstrained binary optimization problem can be solved using the same method, same algorithm. So how can we do this? Firstly, you have to represent our problem as a QUBO. What is a QUBO? Any problem that has all the terms either as bilinear terms or as quadratic terms. So here you can see a bilinear term and a quadratic term is a QUBO. And therefore, it can be represented as a QUBO matrix. X is the X transpose QX, something like this. So X transpose QX, where Q is the QUBO matrix. And again, X transpose QX, similarly as we did before, can be represented on a quantum computer as the expectation value of Q in the state psi, in the parameterized state psi. So again, we have kind of the same formulation. So we just replace the Laplacian L with the matrix Q, and we are good to go. We just have to take care that the Q is Hermitian. So the Q has to be symmetric. Usually there exist ways to represent problems where Q is not symmetric, but you have to make it symmetric so that it works. Okay. An example for the QUBO, how to do it by QUBO, is the maximum weighted independent set problem. So what is a maximum weighted independent set problem? Firstly, what is an independent set? If you have a graph, an independent set is a set of nodes that are not connected to each other, simply. So here we can see in red that these nodes don't have any edges between among them. So that 1, 3, and 5 is an independent set. And by extension, we can see that 1, 3, 5, and 7 is the maximum independent set. So the maximum size of the independent set for this problem. So yeah, so the maximum independent set maximizes the size of the independent set. And then after that, we can have weighted independent sets. That's what we're going to use here, where the nodes have weights, and you have to maximize the weight of the, we have to find the largest weighted independent set. So maximize the weight of an independent set. So here we can see like a fundamental difference with the max-cut problem is that in a max-cut problem, basically you can choose any partition and that will be a solution. Here, for example, not all solutions are even feasible solutions. For example, if I choose 1 and 2, it's not just that it is not a good solution. It's just that it's not even a solution. It's not even a possible solution. So all possible solution is the feasible search space is not the entire search space. That's the main difference. So it's a constraint problem, whereas max-cut was not a constraint problem. So that's the main difference. So in order to convert this into a QUBO, as I said, it's a constraint problem. So we have an objective function. So max sum of weights wi xi. Okay, that's the objective function. And on top of the objective function, we have a constraint. So we have multiple constraints. And all these constraints, we have to, for it to be a QUBO, it has to be integrated into the objective function. So how do we do it? It's quite simple, actually. We maximize it, maximize the objective function, and add a penalty every time the constraint is violated. So here you can see every time the constraint is violated, we add a penalty term P. So how does this work? Let's say, so the only times that P will subtract the term P is when xi equal to 1 and xj equal to 1. So 1 times 1 is 1. So all the other times, because it's 0 and 1, all the other times is going to be 0. And you can see that only when xi equal to 1 and xj equal to 1 will this constraint be violated. So only 1 plus 1 equal to 2. So that's not less than equal to 1. So that's the only time the constraint is violated. And this ensures that it's an independent set. So this is how you can convert a max-weighted independent set problem into a QUBO. And then you can put the QUBO inside in the place of the Laplacian before, and it works the same as before, basically. Okay, so for results, we have 32, 64, and 128 nodes. And we are comparing the normalized cost. So 1 here is the optimal. And you can see that for 32, it kind of finds the best solution every time, but there is a variance. And for 64 and 128, it's kind of degraded the solution. The reason for the degradation is actually the black box optimizers that we use in this case is the genetic algorithm. So the performance heavily depends on the number of how many iterations, how many generations of the genetic algorithm that you use. So basically, I think if for 128 we used more generations, we would have gotten a better solution. But yeah, the idea was to compare with kind of similar number of generations. So it's degrading for the same number of generations. Okay, so that was about the algorithm, the LogQ algorithm, and what basic problems that you solved by using it. And now I go to the use case, under task 5.4 that we had to do mesh segmentation. So firstly, what is a mesh? So any surface can be represented numerically using nodes and faces and edges. So basically using polygons. Using polygons, you can represent a surface as shown here. This is actually the simplest form of a mesh, a triangular mesh. And this is quite useful in computer modeling, and it has several applications like earth imaging, modeling of reservoirs, etc. And here on top of that, you can see there are 2 different types of meshes. This is on the right, we can see a coarse mesh. On the left, we can see a finer mesh. So the coarse one is a worse approximation, and the finer one is a better approximation of the surface, of the actual surface. So the idea of mesh segmentation is to separate different parts of the mesh depending upon the properties, of the mesh, basically. So every node here will have a property associated with it. So in a mesh, every node has a property associated with it. It can be porosity, it can be anything. So, and then the idea is to separate the different parts of it, find different clusters depending on the properties. So that is the what is segmentation is. And to take an example, this is like a 2D mesh. So it's a 2D mesh. It has colors from blue to, it goes from blue to yellow. So the lowest, when it's closer to 0, it's blue, and it's closer to yellow, it's 100, closer to 100. So when I say property, it's just a number. Every node is just assigned a number from 0 to 100, and yeah, it can be 0 and 1 as well. So it can be between 0 and 1. So it's just what we decide. But actually, it's kind of equivalent to put a number between 0 and 100 or between 0 and 1. It's quite equivalent. So in order to solve it, so the idea is to solve this problem using our algorithm to represent this problem on with the LogQ problem, the LogQ algorithm. So how do I do that? Firstly, I have to convert this mesh problem into a graph problem. So it has to be a graph optimization problem. So this is quite easy to see. This is the graph of this one. So of this mesh, and then it's converted into a graph. So every node of the triangle of a mesh is a node of the graph. Every edge of this graph is a side of the triangles. So that's how you just convert it into a graph. And then after that, on the edges, on the nodes, you put weights. So you put node weights that is equal to the property. So for example, on number 63, I will put 100 because it was 100 there, and so on and so forth. I will just put the value of the property on the nodes, and now it becomes a weighted graph problem. And now for this weighted graph, what I need to find is I need to find clusters. So I need to find clusters of so groups, basically groups of nodes having similar properties. That's the idea. You have to find groups of nodes having similar properties. So group them together if they have similar properties. That's the idea. And okay, next we have to define an objective function. Why? Because here what we're told to do is, okay, cluster this problem, but you have to convert it into optimization problem. Now we have to define how are we going to do the clustering. For that, we have to minimize or maximize something. So we have to define what do we need, what mathematical function do we need to maximize or minimize in order to find the clustering that we want. Okay, so for that, we've here in our deliverable, the modularity, the objective function that we use is called modularity. So I'm not going to go too much into the details of modularity. I've cited the paper here. So, but what it tries to do is it tries to maximize the intra-cluster density. So inside the cluster, it will try to maximize the number of edges. And outside the cluster, and in between the clusters, it will try to minimize the number of edges, simply. So that we have more and more edges inside a cluster and less edges outside a cluster. So to form closed clusters. Okay, and as defined here in this paper, this algorithm is only for bipartitioning. So it does not do more than 2 partitions. That is a significant shortcoming. And we do multiple partitions here, and that is only that what we do is we repeatedly bipartition it. So of course, this limits us to 2 to the power n partitions. So we do 2 and we bipartition again and we get 4, and we bipartition again and we get 8, and so on and so forth. So it is possible to do a generalized definition of modularity. I defined a generalized modularity in my thesis, but I did not work on it further. And but it would require more variables and more qubits, and it can be something that's interesting to see in the future. Okay, so for results, so we did multiple sizes. We did 34, 32, 64, 128 as well. And we did for many segments, 2, 4, 8 segments. And we have put all the benchmarks are in the deliverable directly. But I just wanted to show a graphical representation of what our results look like, so that it's easier to see. So you can see in k-means, it does a perfect clustering with none of the clusters are separated from each other. And here it's LogQ. It does relatively well, but you can see 122, 123, a lot of, some of them are mixed between each other. So it's not perfect, but it's still getting there. So we can improve on this. But the problem is, as I said, it's only bipartitioning. So the results get worse when you have multiple segments. So you have here, there are multiple segments, you have 8 segments, and you can see it's kind of all over the place. The yellow one is a bit split. The blue one is a bit split as well. So yeah, it's not great results, but yeah, it's a proof of concept, and we can try to improve upon this one. So takeaways. Takeaways are, for the mesh segmentation, we did a proof of concept, got up to 128 nodes for 2, 4, and 8 segments, and all using 8 qubits. So we have to remember that. So all using 8 qubits. And yeah, as we saw, the results were relatively decent for bipartition, but the segmentations are getting worse quite significantly with the number of segments. So the future work would include finding a generalized modularity. Well, as I said, I've already defined it in my thesis, so you'll find it in a few months, I guess. And then there is a different objective. So, well, you can we can try to think of a completely different objective function, which can be anything, I don't know, but yeah, which might improve performance. Okay, so finally, conclusion. Using LogQ, so you can find this method has been published in Physical Review A. You can find it here. Yeah, using this encoding, we represent many problems, many NP-hard problems, and we use much fewer qubits and we represent it on a NISQ quantum computer. And secondly, we tested a couple of use cases. So firstly, it was a mesh segmentation that I presented here. There's also another use case, fleet conversion use case, which is also under review in another paper, in another journal, and you can go and see it if you're interested. I think it's quite interesting work, and we show how to use quantum computers in a hybrid manner with classical solvers like Gurobi. And then finally, for the deliverables, for deliverable 5.9, we have already submitted it, and 5.11, which is the codes for the LogQ and how to solve mesh using LogQ, and that will submit it. We're gonna submit it later this year. So thank you for your attention, and yeah, that's all.
Thank you, Yannick. So now is the time for questions. So I'll share my screen first. Yeah, okay. So we have a couple of questions in the chat already. So Yannick, I suggest you open the chat. We have two questions from Laurent Querella, who is one of our regular attendees. Hello, Laurent. So first question was asked fairly early in your presentation, Yannick. And does such a relation, objective versus Laplacian matrix, exist for other problems than max cut?
Yes, so indeed, indeed. So as I explained a bit afterwards, that we represented other problems using QUBO. So yes, like actually, if you find the QUBO of max cut, it's a Laplacian. So it's kind of like this. It's kind of in later we generalize it as a QUBO. So yes, basically, the answer to your question is yes, and it is a QUBO for that problem. Yes.
Okay, so next question from Laurent was how modularity is taking into account the node weights in the objective function.
Yeah, that's true. That's true. The answer it doesn't, and that's probably why the results are not good. And it's something I was thinking about yesterday when preparing for this presentation, actually. So it's yeah, you're right. It does not, and maybe and actually I cannot share my screen anymore, I think, but okay, doesn't matter. Actually, if you can actually this kind of you can see this in the results, because you can see it clearly for two partitions kind of the k-means is doing it according to the values, like along the diagonal, but for us it's just along the center. So this clearly means it's not taking the node weights into account. So yeah, thank you for that comment. Yeah.
Okay, then we have a message from Mariamo Musa. Hi, thanks. We also have some questions. Do you want to ask your questions in Thank you, Laurent. Do you want to ask your questions in the chat, or do you want to ask them? You can activate sound. I think you can. Up to you.
Do you hear me?
Yes, we can hear you.
Yes.
Please
hi.
go ahead.
Yanni, thank you for your talk. I have two questions. The first one regarding to the complexity of mapping your Lagrangian to Pauli strings, because in some problems I assume that it's a dense matrix and it involves like n to the power n Pauli strings to
it's 4 power n. Yes, you're right. So I did not. Yeah. finish your question and I'll answer.
Yeah. That's the point. It's not a drawback of the technique.
Absolutely, I absolutely like that you asked this question. It's a very, very good question. So yes, I did not talk about the drawbacks of the problem of the encoding, and indeed, the main drawback is that in order to map it, I didn't talk about it during the overview, but in order to map it, you need to convert the operator into a sum of Pauli strings, absolutely. And then during my PhD, actually, I did not really take care of this, and it was only during the end of my PhD, because it's just a line of my code, and as I did larger and larger tests, I figured out that okay, this is contributing the most to the complexity. So I didn't get time to do research on this, but the idea is we did read some papers. I read some papers, and it's like basically if the matrix is kind of not that dense, we're kind of able to represent it by some methods like Berry, etc., and represent it using few. Well, the complexity is kind of reduced in order to represent it as a sum of Pauli strings. But yeah, you're right. This is a main drawback. So that's the kind of the future future ways to research it. That's it. Thank you for your question. Very good.
Okay, and I have another one, which is
Go ahead.
surprising to me, which is how do you know which your ansatz, your parameterized unitary U has enough expressibility? Because it's very simple, no? How do you know that it will
represent all my solutions? Is that your question?
Find the best fit the parameters to find the minimum energy or the cut or whatever.
Well, the idea of the ansatz was just to represent all the possible solutions. So using all the parameters, it does represent all the solutions. It represents all the vectors 1, -1. So by extension, it represents all of the solutions. So in what sense do you mean?
Yeah, and well, it represents all the solutions, but
yes,
how do you have a clue of there is a set of parameters that will select the minimum, the optimal cuts? Or
yeah.
I don't see that point.
Because the parameters are then fed to the black box optimizer.
Yeah.
So and then
more complex unitaries will do better.
Okay.
Does not make sense, or that's the perfect answer for your problem.
So you think that, well, my idea was I will represent an ansatz to represent all my problem, but what you're saying is if I try more complex ansatz, but okay, if I try more complex ansatzes, it will be better. It will be better. But in what sense complex? Can you just explain a little bit, if you can?
Yeah. Well, the typical QAOA supports in the adiabatic principle, in the adiabatic theorem, and that's why it takes a mixer, which is the X mixer, and initializing the Hadamard gate. So I don't see the mapping of that problem to your problem. Yeah,
the thing is the problem is not mapped by the problem is not mapped on the ansatz. The ansatz just represents the solutions. The problem is mapped on the Hamiltonian.
Yeah.
When you find the expectation of the expectation value of the Hamiltonian gives the cost function. So the Hamiltonian in let's say in Laplacian or the QUBO, that would represent the problem. So the ansatz does not map the problem. That's it. Like the ansatz only maps the solutions, like the solution space.
Yeah.
That's it.
Well, Thank you. If I have any other doubts, I can contact you.
Yeah, just send me an email if you have any other doubts. No issues.
Okay. Thank you very much.
Thank you, Mariamo. Do we have any other questions from our audience? No? No questions? Okay. Well, if you think of more questions later on, I mean, you're very welcome to send an email to the contact address in the.
Sorry.
Yes.
We have another one question.
Yes.
Oh, please go ahead. We have time.
Yeah. We are a group listening to you, so you will listen different voices. I am Mariamo, actually. I have a question related to the last one and the complexity of the problem. So your ansatz, what's the density of the connections in your problem, and what this could affect to the execution in a real quantum computer? Janet, so.
What is the density? I mean, well, for meshes, as I said, like if the matrices are have low density, they can be found. There are more, let's say, smarter ways to decompose it. But I think if you just find in a brute force manner, the complexity is, I think, v². So where v is the number of nodes. So that is the complexity to find all the terms, all the terms of the Pauli strings. So that is the added complexity, indeed. And
sorry. Yes, carry on. Sorry.
Yeah, that is the added complexity, v², where v is the number of nodes, or v² n square, and that is the main shortcoming, as I said. And if it's a fully dense one, so if it's like, so for mesh, for example, you can see it's not fully dense, and even for the weighted independent set, it is not fully dense. So you can try to find smarter ways to decompose it. But for example, in the partition problem, it's a fully dense graph. So I think there is no way out of it. There is a added v² on the complexity side.
Yeah, there was an initial graph plotting mass cut versus density, and
yeah,
I'm curious about what that metric means.
What that metric, like,
yeah, okay. I don't understand the graph. Sorry.
What is density? Okay, density. Okay, sorry. Yeah, sure. The density is just the number of the total number of like the number of nodes. Sorry, the number of edges. The ratio of the number of edges divided by the total number of possible edges. That is density.
Okay.
So the total number of possible edges in a graph of n nodes is n into n minus 1/2. That is the total number of possible edges. So it is just the ratio of the actual number of edges on a graph by the total number of possible edges. That's it.
And that plot that is max cut versus density, what is measuring the max cut?
What is measuring the max cut? It's the value of the objective function. Okay. And I think it was normalized. So 100. So in normalized means, so of course for different problems, the value of the optimal value of the cut will be different. So it's normalized to make 100 the maximum. So it's like as a percentage of the optimal value. So we actually calculated the optimal on a classical. We wrote MILP to calculate the optimal, and then like MILP on a classical solver, and then we computed the difference. So that's how we computed it.
Okay, I see. Understood. Thank you very much.
You're welcome.
Okay. May I ask where you are based?
Yeah, we work at CESGA. That is a supercomputing center in Galicia, in a region of Spain.
Yeah.
Yeah, we are like
CESGA, you're one of the NISQ.
Yes.
Okay.
Yeah.
Yes.
Well, it's good to have people who are, well, you're from one of the project partner, but obviously I don't think you're in the project. I mean,
No,
you
we are
personally,
not.
so it's nice to know that the information is spreading to
Yes.
other people and other teams. Good.
Yeah. Yeah. Thank you very much.
Well, thank you for your questions. I mean, that's why we are organizing this type of webinars, to be able to discuss and exchange with other people. So thank you very much. Any other questions, or can we close now? No? Okay. Well, in that case, I would like to thank everyone, and especially Yannick for his presentation, for sharing his research. As you see, it raised a lot of interest, so that was good. If you're interested, we have our next webinar is not in August. We're on holidays over the summer, but on the 3rd of September, we'll have a webinar dedicated to hard optimization problems for smart charging of electric vehicles, and the speaker will be EDF. Thanks again, everyone. Have a lovely summer, and hope we'll talk to you in September.
Goodbye.